Okay, now we will see the third image parameter. After image impedances and iterative impedances, we have the one which is characteristic impedance. So this is the impedance which is generally the characterization of any transmission lines. So any transmission line will be having a characteristic impedance which will be specified. You might be coming across with this in your transmission line course, fine, but we will see what it is. So it says that when the image impedance of a network becomes equal to the terminating impedance of the network, then that impedance is known as characteristic impedance, right? So we will see how to derive this. So that means we have a network and we have an output impedance for that network, and if that Z0 is same as that of Zin, then we can say that Z0 is nothing but characteristic impedance. Fine, right? So now for a symmetrical T section we will be deriving it. So this is Z0 and we have a symmetrical T section. Note that here I am not considering them as Z1 and Z1. I am considering them as Z1 by 2 and Z1 by 2, just to make the overall series combined resistance or impedance is Z1. With that purpose I am considering this. Sorry, it is considered like this, and the shunt component impedance is Z2. Right? For this T section, which is symmetric, we have characteristic impedance, right? That is Z0 is the terminating impedance and Zin is there, which is equal to Z0. So this condition will be used here for deriving Z0, right? So you can see that here. So what is Zin now? Zin is here Z0 and Z1 by 2 are in series, that is in parallel with Z2, and that overall combination is in series with Z1 by 2. So that is only written here. So which is equal to Zin. Zin is nothing but Z0. So it is equated to Z0. Now we have one equation where Z0 is only unknown. All others are known, because for a given network, the network parameters of impedances will be given. Right? Fine. Then what is Z0 here? Z0 is equal to square root of Z1 square by 4 plus Z1 Z2. So after simplifying this, you can easily get this Z0, right? So similarly we can even determine Z0 for pi section, right? So this is based on the definition of Z0. So if you observe, in case of image impedances, based on the definition we got image impedances. After that we also got them through open circuit and short circuit impedances. So that can also be done even with Z0 for Z0, right? So since characteristic impedance is for symmetrical networks and there won't be Z1OC, Z1SC, Z2OC, Z2SC, they are equal. That means open circuit impedances as well as short circuit impedances are equal for symmetric network. That means they are equal to one open circuit impedance and one short circuit impedance. That's why we will not have any Z1OC, Z1SC, Z2OC and Z2SC. Here you will have only directly Z1OC and ZSC, sorry, ZOC and ZSC, right? Because they are equal for both ports, because it is for symmetrical network, right? So Z0 is equal to square root of ZOC and ZSC, that's it, right? So we can also determine characteristic impedance using this formula. So if you do that for this particular network, you will get the same Z0 value. So like this we can verify it. Okay, fine. This is about characteristic impedance. Note that characteristic impedance is there for symmetrical network only, right? If it is not symmetric and this condition is happening, then we will call them as iterative impedances, like how we have seen it in the previous parameter. Okay, that's why I told in that lecture, note that it is not a symmetrical network. If it is symmetrical network, then what will be there? If Z0 and Zin are equal, then it is called as characteristic impedance, not iterative impedance. This is very important distinction here. That's it. Thank you.